Good day and welcome to everyone to our presentation today on cautiously counting crocodiles. The background to this project was to aid in crocodile management and conservation efforts through non-invasive population estimates. Existing methodologies of counting crocodiles are problematic, such as loud aircraft and helicopter scaring crocodiles, or capture-recapture being stressful to the crocodiles. Counting crocodiles even in breeding pens can be difficult, which is often based on old counts plus some data, which can diverge over time. Drones are less disruptive, but manual counts on the produced images are labor and time intensive. There is also an identified need to standardize counting methodologies across crocodile farms in South Africa. The goals of our project was to develop a computer vision model to localize and count crocodiles in UAV imagery, as well as extract additional data. The data that we were working with was the raw JPEG images collected by the UAVs, as well as georeferenced TIFF files. The challenges that we encountered was a lack of annotated data, which is required for training supervised machine models.
Okay. In terms of our research methodology, we attempted the easy approach first. We identified a research study by researchers based at an Indian university looking at mugger crocodile identification using a YOLO V5 model. The fine-tuned approach as well as a zero-shot transfer approach was tested. However, the results were unsatisfactory. The main conclusion was that the variance in altitude, as shown in the images below, contributed to the unsuccessful identification of the crocodiles in our study. We then evaluated the YOLO V8 and faster RCNN-based model architectures. We varied the data set looking at farm only, wild image only, as well as a combination of farm and wild images. Initial experiments only focused on the localization of the crocodiles. We used this to identify our best performing model, which was the Detectron 2-based mask RCNN model, and thereafter focused on key point extraction. As we can see, we annotated the snout, neck, and vent of the crocodiles, and we annotated approximately 70 drone images. Originally, we only had Crocodile Farm A at our disposal. We used these annotations to train a model and tested out the generalization on Crocodile Farm B, which we received later on. The generalization was found to was found to generalize well, and we subsequently decided to enrich our training set using the Crocodile Farm B images.
Okay, as was discussed in the previous slides, the transfer learning approach failed to generalize. While our model is not perfect, it does perform fairly well. It does produce false positives, which is phantom detections, and it also does produce false negatives, which is misdetections. And as we can see from the graph on the right, our model does seem to be slightly more prone to false negatives than false positives. We also found that our model is sensitive to altitude, and as previously discussed, the model was validated to a different environment, Croc Farm B, before the training data was enriched, as well as with correlations with established Nile crocodile metrics, as will be shown in the following slides.
We then deployed our web app based on Gradio. We allowed the user to specify the model confidence threshold, trading off the false detections and misdetections. The user was also allowed to specify the file input format. The web app indicates the total number of crocodiles detected in the uploaded image, as well as a few additional visualizations, including the bounding box size distribution, correlation between our identified crocodiles and a snout, neck length, snout, hind limb length relationship identified in literature. As we can see, we find an R-squared value of 0.4. We also look at the crocodile neck mobility, which is the angle between the crocodile's head and its body. Processed the large georeference GeoTIFF files in patches of 2000 by 2000 pixels. One of the limitations is that we could possibly miss crocodiles at the borders of these patches. However, processing the TIFF files allows us to use real measurements such as meters and centimeters. One of the key requirements from our project partner was the ability to produce Esri-compatible shapefiles. We can do so directly from our web app. And as we can see in the image below, the shapefiles can be visualized in our project partner's preferred software. Thank you very much for listening to our presentation, and we welcome any further questions.